All right, a 0.2 kilogram object moves along in a straight line. The net force acting on the object varies with the object's displacement. Now, once the force starts varying, what happens to the acceleration? It starts varying as well. And so during this period here from 12 to 20 meters, where we have varying forces, you can't use your kinematics equations. Because remember, the kinematics equations are only good for constant accelerations. If the force is changing, the acceleration is changing, so you can't use them. Problem. The object starts from rest, and displacement x equals 0, time equals 0, and displaced distance is 20 meters. Determine all of the following. Acceleration when we're at 6 meters. So we'll take a look at 6 meters. Force is 4 newtons. So F equals ma. Force there is 4 newtons. Mass of the object is 0.2 kilograms, as read from the problem. Acceleration 20 meters per second squared. Time taken for the object to be displaced, first 12 meters. What do you think? Kinematics. Since you know the constant acceleration of 20 meters per second squared, you know initial conditions, velocity 0, you know displacement is 12 meters, a lot of kinematics information, so you go there first. Change in x, v naught t, 1/2 t squared. Displacement is 12 meters. Initial velocity is 0, so that all goes to nothing. 1/2 the acceleration, t squared. Time, 1.1 seconds. Yeah, you can leave it in any non-simplified terms if you want. If you have a calculator, go ahead and do it out though. Yeah. Or simplify it down to say square root of 1.2. That's better. As simplified as you can get it is preferred. Amount of work done by the net force in displacing the object 12 meters. So, work, change in x. Force applied over that first 12 meters is 4 newtons. Distance, 12 meters, 48 joules. Okay. Now, we get into more complicated questions. Speed of the object at displacement 12 meters. Well, if the first thing you think of is kinematics, you'd be fine. You can do the kinematics equations to find velocity. Initial velocity is nothing, twice the acceleration, 12 meters, 21.9 meters per second. Kinematics works fine. If that's the first thing you think of, go for it. There's an alternate method using what we've been learning here. The work-energy theorem. Once we know how much work that is done on something, we can find out speed. The work done on the object causes a change in kinetic energy. The initial kinetic energy is 0, so what happens at the work is just equal to the kinetic energy that it ends with. So work equals 1/2 mv squared. That's the work-energy theorem. The work done, we calculated already. That's the area under the curve. 48 joules. Velocity, 21.9 meters per second. So either way, yes. Where'd you get time? Yeah, I suppose you can. That is overlooked by me. That one too. So or. Three ways of solving that one. That was the last one I thought of. That's ugly. That is far simpler than anything else, but it's good to practice the other methods too, especially this one since we're working on this. Especially since you can't solve part E without that. Well, you can, but it's much, much more difficult. There's a couple ways to solve part E. Well, you could find the average acceleration and use that, but that's going to be a complicated way to do it. The best way to solve part E here, the final speed of the object at 20, is using the work energy theorem. Now, in order to do that, you need to know how much work was done over the whole thing. So we know that this is 48 joules. So how much work was done during this part? Work is the area, 1/2 base times height. Meters, 4 newtons. 16 joules of work was done there. So the total work done during that entire process is 64 joules. Now the work energy theorem states that that work done is going to be equal to the change in kinetic energy. The final kinetic energy minus the initial kinetic energy. Once again, the initial kinetic energy is 0 because it started from rest. So the work, 64 joules, 1/2 times the mass times the final velocity of the object squared. Solve for that. It's 25.3 joules per second. Any other ways? Yes?
Velocity final squared equals the 21.9 squared.
Okay. Yeah. The average acceleration, since we're going from, well, you need the time too. You went through and calculated average acceleration for that interval.
For the equation,
How did you get the acceleration?
I just, since it's half of the force of the other section.
Okay. Yeah, average force, you got 2 newtons for the average force. 0.2 mass, so 10 goes in there for A, yeah. So you could also do this. Final velocity equals initial velocity squared plus 2 average times change in position. Yep. So work energy theorem or find average acceleration. All kinds of different methods for solving that particular question.